the example that your text talks about with the one-way ANOVA. So far we have discussed how it's different than a t-test, and we've talked a little bit about what it's doing behind the scenes, how it is parsing out the different sources of variability, and using that to determine whether there's a significant difference between the treatment conditions, okay? So the example that your text uses is this food maze study. So Dr. Chung is interested in whether food can help really motivate these rats to find the end of a maze, okay? So they've got 10 rats total, and Dr. Chung randomly assigns these rats to 3 treatment conditions. There's a low-calorie condition, a normal calorie condition, and a high-calorie condition. So the idea is that, think of it in human terms. A low-calorie condition might be something like a plain salad, something that's not very exciting, something that we're not really motivated to eat. A normal calorie condition might be something like, I don't know, maybe a turkey sandwich. And then a high calorie condition might be something really decadent. So, whether it's a pizza or some sort of fudge sundae, I don't know, whatever it is that motivates you, or whatever it is that you really, really like, that would be the high calorie condition, okay? So same things with rats. You can actually change their diet, alter the calorie content of the food without altering the actual amount of food you're giving them. So that's what they did. In these types of studies, you want your animals to be food deprived to a degree, because if they're not hungry, they're not going to be motivated by food, period. So rats are going to be put on a diet until they're 10% of the normal body weight, and then they're put in those 3 treatment conditions. So essentially, the animal is starting in one point in the maze, and they're timed to see how long it takes them to get to that goal box. So we would hypothesize what? That the more decadent the food is, the more rewarding that food is, the more you want it, the faster you're going to go get it, right? So over time, you're going to see that that rat is going right to that high-calorie food source. So here's the data. And what we have are the 3 treatment conditions, the low, medium, and high-calorie food groups. This is the average amount of time in seconds it took each rat to find that food reward. So rat number 1 in the low-calorie group took 30 seconds on average to find the food. Rat number 2, it took 31. 3, it took 32 seconds. In the medium calorie group, there were 4 animals. The respective times it took were 28, 29, 27, 28. High calorie group was 24, 25, 26. You also see down here are the sums of each treatment condition. So sum this, you get 93. Sum those 4, 112. Sum these 3, you get 75. You get the N right here of each treatment condition, 3, 4, and 3. And then I've got the mean calculated right here. So what we see is that in the low calorie group, it takes on average about 31 seconds for the animal to find the goal. And then it goes down to 28 seconds. And then finally, only 25 seconds to find that high calorie food reward. And then lastly, the standard deviation. So we know that we can't simply go by means, because there might be other factors contributing to these mean differences. It could be due to chance alone. So we have to look at a statistical test to determine whether these means are truly due to the independent variable, the type of food the animal received, or if the mean difference is due to simply chance alone. So I want to call your attention just quickly to a couple of things. In the last video, we talked about between group differences and within group differences. The between group difference here is illustrated by the differences in the means. All right, 31 versus 28 versus 25. That's the between group difference. The within group difference is illustrated by the variation you see in each treatment condition. So here we have 3 rats perform similarly, but there's variation here, right? And here we have 4 rats similarly, but there is variation, and the same here. So we have within group variability in each treatment condition. So what ANOVA needs to do now is look at that signal to noise ratio and determine whether that signal is greater than the noise to determine whether there's a difference between those groups. So if we want, we can put our data into a bar chart, a bar graph, and you can see that data very nicely. So we're going to pick our test. We're comparing the means of 3 independent samples. We automatically know we're not going to do any of the tests that we've learned before. We can't do a t-test, any of the 3. We're not going to do a z-test, right? So we're going to do an ANOVA. So we're going to check our assumptions. We have 4. We have random samples. We've talked about a million times. We have independence of cases. We've talked about that. We have normality and also homogeneity of variance, simply meaning that within each treatment condition, we should see variation that is relatively similar. So if we go back to the slide, we would violate homogeneity of variance if we saw some really wild scores in one group relative to the other. And we can kind of tell that it's satisfied based on the standard deviation being relatively similar across groups. So when we list our hypothesis, or step 3, it's important for you to know that with ANOVA, it's always non-directional. Remember, there's directional and non-directional hypotheses. With a t-test, we could choose which one we wanted to do, because we could choose whether one group is going to be greater than another. In ANOVA, you have more than 2 groups, so it could very well be that one group is going to be greater than another group is going to be lower than another. So because of that, we always do generic non-directional hypotheses. So our null is always going to be written as such. The mu of population 1 is equal to 2 is equal to 3, because we have 3 groups in this example. And then our alternative is always going to be written in plain language, and it's simply that at least one population mean is going to differ from another. So we're going to set our decision rule. ANOVA is a distribution that starts at 0 and extends to the right, so it's always going to have a positive value. So we have to figure out what our critical value of f is going to be. And to do that, we have to get some data from our study. First of all, we need to think about how many groups we have. All right, in this example, we've got 3 groups. And we're going to now label the number of treatment conditions with the letter K. So K is equal to 3. We also need to think about how many participants we have in the study altogether. And the total sample size, the capital N, is 10. Okay? So using these numbers, we're going to find degrees of freedom. And essentially what we're doing is we're finding the degrees of freedom for our within and between subjects variability. So our between subjects degree of freedom is equal to the number of treatment conditions we have minus 1. That makes sense because between subjects is really referring to between groups. So group 1, group 2, group 3. So it's 3 minus 1, and that's 2. And that's always our signal, so that's our numerator degree of freedom. And then our denominator degree of freedom, that's our noise. And that has to do to individual differences, right? So we have 10 individual cases. So 10 minus 3 conditions is 7, okay? And that's the denominator. So we go to the back of the book, look at the appendix, and we find the critical value for 2 and 7 degrees of freedom. And we find that it's 4.737. So what we know now is that when we calculate the value of f, if our value of f is 4.737 or greater, we have found a statistically significant effect of food on the amount of seconds it takes to find it. So we're finally at the part where we're going to calculate the test statistic. And I'm not going to have you do it all by hand. This is a pretty laborious statistic to do. I'm going to give you some of the data, but what I want you to understand is how to read these tables. This is an ANOVA table, all right? And it's commonly provided in the printouts that you get if you're running the analysis using SPSS or another statistical program, okay? So I want you to be familiar with this, and I also want you to be able to calculate the value of f using this formula. The value of f is ultimately the mean square between and the mean square within. Now, mean square is a new term that I'm introducing, and really it's just a fancy word for variability. So ANOVA is analysis of variance, so we're analyzing the variance or variability of the between groups versus within groups. That's what we're doing. All right, so here's our ANOVA table. I'm not going to get into all this. Whole lot of stuff. So let's go right to the chase and let's look at the data. So essentially, what we're calculating are sums of squares and degrees of freedom. This is the more tricky part to calculate. But once you have the sum of square, it's really easy to find the mean square, because a mean square is simply a sum of square divided by its degree of freedom. So 54 divided by 2 is 27. 6 divided by 7 is 0.86. And then you have the total here. I always fill this in, but it's not necessarily important when finding the value of f, because f is equal to a mean square within, a mean square between divided by the mean square within. So 27 divided by 0.86 is 31.40. So there's our observed value of f relative to our critical value of f. So clearly we reject the null. And what we do is state it in APA format. So f for 2 and 7 degrees of freedom. Remember, this refers to our between subjects degree of freedom. It tells the reader that there were 3 treatment conditions. And this is our within subject degree of freedom. This tells the reader that there were 10 groups, because this plus the 3 groups equals 10 participants. So this tells readers there were 10 participants. So f for 2 and 7 degrees of freedom is 31.40. The null was rejected at the alpha level of 0.05. So what we do then is answer 2 more things. We always answer, what is the effect size? So how sensitive is the animal's behavior of finding this goal food to the calorie content of the food? So what we're going to do is calculate R squared. Super easy to find, because like always we go back into data we already have collected. In this case, we go back to our ANOVA table and we take our sums of square between, we divide it by our sums of square total, and we use that to calculate a percentage. So in this case, we have 54 divided by 60, and our effect size is 90%. That's a huge effect size, okay? So that tells us that 90% of the variation that we see in those scores, meaning the number of seconds it took to find that goal food, 90% of the variation we see is due to the food itself. Only 10% of the variability is due to something else. So this is a huge effect size. So we know that food impacts behavior, right? We know there's a significant difference between the groups, but one thing ANOVA does not tell you is where the differences or difference lies. So in the next video, I'm going to talk to you about what's next, and it's going to be post hoc tests. In the meantime, if you've got any questions, let me know. You can email me at asikorsky@tamet.edu.